All right, we're going to take a look at an example here that allows us to work with our three new equations that we just derived. So it says you kick a soccer ball at an angle of 40 degrees above the ground with a velocity of 20 meters per second. Determine the following: the maximum height of the ball, the time of flight, and how far you were able to kick it, aka the range. And then finally, the final velocity when the ball hits the ground. Okay, so using our new equations, let's do A first, which allows us to look for the maximum height. So our new equations say that h equals that initial velocity squared times sine squared theta all over 2 times gravity. Okay, so remember, for all of these, what we're going to be able to do is say that the initial velocity is simply just equal to 20 meters per second. Okay, the angle that we use is 40 degrees. Okay, and remember, g, for the purposes of this, you're going to use positive 9.8 meters per second squared. Okay, I considered the negative portion of it when we were doing the derivations, so that canceled it out, and now you can just plug in your positive 9.8 for all of these. Okay, so now that we have those, we literally don't have to do anything else other than plug in everything. So our initial velocity was 20 meters per second squared times sine squared of 40 degrees, all divided by 2 times 9.8 meters per second squared. Okay. So your 20 meters per second all squared works out to 400 meters squared per second squared. Okay, and sine squared 40 is 0.41318. Okay, so when you do that in your calculator, you just do sine of 40 and then you square that value. Okay, and that all gets divided by 19.6 meters per second squared. Sorry, this is meters squared per second squared. So now your meters squared canceled out, your seconds squared canceled out, leaving you just with meters. Okay, and when you do 400 times 0.4138 divided by 19.6, we get an answer of 8.432 meters. Okay, so the maximum height is 8.43 meters, and then we indicate that direction up. Okay, so that's it for the maximum height. Notice it's a lot nicer to use than breaking it down into components and finding your maximum height that way. All right, now we're just going to find the time of flight. We can use all these same variables for our time of flight. Okay, and from our derivations, the time of flight equals 2 times that initial velocity times sine theta all over g. Okay, so we get 2 times 20 meters per second times the sine of 40 degrees all divided by our g, which is 9.8 meters per second squared. Okay, so I get 40 meters per second multiplied by sine 40 comes out to 0.64279. Okay. Divided by your 9.8 meters per second squared. Your meters cancel out. One of your seconds cancels out, leaving you with 1 divided by seconds, so that converts to seconds. Okay, so the time that I get is 2.6236 meters. Or sorry, not meters. We're looking at time here. 26 seconds. So if we go to our significant figures again, the time of flight is 2.62 seconds. Okay. And then last but not least, we're going to do how far were you able to kick it, or the range. And our range equation that we just derived is equal to that initial velocity squared times sine 2 theta. Okay. All over g. Okay, so remember you can use the exact same variables again. So we get 20 meters per second all squared times sine of 2 theta, which is 40 degrees, all over your 9.8 meters per second squared. Okay, so your 20 squared again works out to 400 meters squared per second squared. Okay, and that gets multiplied by sine 2 theta means you have to multiply the 2 by the 40. So then you're taking the sine of 80 degrees. Okay, and then that's still divided by your g of 9.8 meters per second squared. Okay, so you end up with 400 meters squared per second squared times sine 80 is roughly 0.98481 divided by your 9.8 meters per second squared. Okay, and again, your second squareds are going to cancel out. One of your meters cancels out, leaving you with meters. Okay, and we get an answer of 40.1962 meters. So the range is 40.2 meters forward. Okay. And then last, D asks us to solve for the final velocity. Okay, as the ball hits the ground. Okay, so we would normally break it down into components here, but let's just look at the situation again. Okay, if we look at our initial velocity, it goes up, it's going to come down. Okay, and remember, because that dy is 0, we have a very symmetrical situation here. So the angle that you make with the ground for both of them is going to be the same. Okay, if that angle is the same, notice what else is going to be the same. Your component in the y direction is going to be the same, just in the opposite direction. And that x component never changes. Excuse me. Okay, so since the projectile was both launched and lands at the same height, we know that dy is going to be 0, and the initial velocity equals the final velocity for both our components. So there's no point in even breaking it down into components and putting it back together. We can say, because of that fact, that the final velocity is simply going to equal 20 meters per second at an angle of 40 degrees above the horizontal. Okay. If you want, you can break it down into components and go and actually solve for the final velocity. But I promise you, if you do, you're just wasting your time. Okay? So we can use all those facts to say that the final velocity is going to be equal. And notice how much more time that saves knowing this situation and using our derived equations, solving for all 4 of those variables. Okay? This is Wanny signing off, and the proof is in the pudding.